Hi everyone. So in this video I am going to show you how you can look at empirical CDF and compare it to a theoretical CDF if you plan on fitting a specific distribution to your data for drawing inference. So let's just begin with the discrete distribution and what a cumulative distribution function looks like or what it actually means. So if you imagine a simple event, say you flip a coin 3 times, so the possible outcomes that you can have is head or tail. We can quickly generate the probabilities in R using D binom function for that. So D binom is going to generate these probabilities. There are 3 flips, so size is 3, and probability of getting head or tail in each flip is 0.5. So these are the probabilities. So the function that is used to generate these probabilities is often referred to as density function, hence the name D. D stands for density. Distributions that generate probabilities for discrete values, such as binomial in this example, are sometimes called probability mass function or PMF. Distributions that generate probabilities for continuous values, such as normal, are called probability density functions. However, in R, regardless of PMF or PDF, the functions that generate these probabilities are known as density, so you will always see a D in front of the short form of the name of the distribution. So like D binom, D norm, D chi-square, stuff like that in R. That's what the nomenclature in R is. So if you want to quickly visualize the probability distribution with a bar plot for the above experiment, that's how it's going to look like. So probability of 0, 1, 2 or 3 heads. That's the probability. Now you can accumulate these probabilities, and their plots are called step functions. These probabilities that accumulate as we move from left to right along the x-axis is a probability distribution. The distribution of these probabilities is known as cumulative distribution. Again, there is a function in R that generates these probabilities, and I have also posted a video which talks in detail about PDFs and CDFs and PMFs and cumulative distribution functions. So instead of D in front of binom, we will put P now. The plot is sometimes called a step plot because as soon as you see, you will see that it is in steps. As you hit a point on the x-axis, you step up to next probability. The probability of 0 or less, for example, is 0.125. Then probability of 1 or less is 0.5, 2 or less is 0.875, and then it is 1. So we can use this little code here to plot this, and as you can see, it's a step function. So 0 to 1, it is 0.125, and as soon as you hit 1, you go to 2, which is you go to the probability of 1, 2 or less, which is 0.5. So we are up here at 0.5, then we are at 0.875, and then the last one is 1, probability of getting 3 or less. In case of continuous distributions, the D binom is basically the mathematical formula to draw the line or this curve. D in front of the norm is for density function. If you don't give any mean and standard deviation, it will by default plot the standard normal with mean 0 and variance 1. The form and the arguments say draw this curve using values x ranging from -3 to +3. So that's what this standard normal curves looks like. That's all what we have done using this command here. The curve is smooth line, which means it's probability distribution for all real numbers. The area under the curve is 1 because it's PDF or probability distribution function. Imagine reaching into this distribution and drawing a number. What is the probability of getting, let's say, less than 1.1 or whatever that number is, right? It is the probability of getting an exact number is essentially 0 because there is 1 over infinite chance of selecting it. Why is infinity in the denominator? Sorry, there is a typo here, because there is an infinite number of possibilities, right? The y-axis values don't represent probability, but rather density. The density is essentially the probability of a small range of values divided by that range. Remember, we don't use normal distribution or any continuous distribution to get exact probabilities. We always get probability of x less than or greater than or in between some values, right? We use some sort of range. For example, what is the probability that x is less than -1? And as you can see on this graph, you can use mosaic plot to do that. That green area gives you the probability of x less than -1. So basically it is showing cumulative probability, right? Sorry, this green region is equal to 0.158, and the probability that we draw a value of -1 or less from this distribution, that's what is given by this green region. Recall, if we use the cumulative distribution function to get this value, we can do that. To visualize all cumulative probabilities for standard normal distribution, we can again use the curve function, but this time with p-norm, just like we did in p-binorm. And if we look at -1 on the x-axis and go straight up to the line and then go directly left to the x-axis, it should be, so if you do this, this area should be exactly 0.1586, just like this area, green area here. So we can use this little code to plot the cumulative distribution. The second line isn't doing nothing, second and third lines in the code are doing nothing but creating these lines, or the segments, blue and the red segments. So that's the shape of a cumulative. It's like an S, elongated S shape for cumulative. So these are the cumulative distribution, actual cumulative distribution function. Now let's say if you observe a data and you think it's coming from normal, you can plot the empirical curve and then compare it with this one to see if it is actually really normal, or maybe you think it follows chi-square with one, so you can do that. So what is empirical cumulative distribution? The cumulative distributions we explored above were based on theory. They are theoretical. We use binomial and normal respectively to calculate probability. In real life, however, the data we collect or observe does not come from a theoretical distribution. We just have some good enough reasons to believe that it might follow this such and such distribution, right? So we use the data itself to create its cumulative distribution. That is what is empirical distribution. So an empirical distribution function, also called empirical CDF, ECDF, or sometimes just EDF, is basically the same thing as the theoretical one. They are both probability models for data. However, while the CDF is a hypothetical model for distribution, ECDF models empirical or observed data. So it is the probability distribution that you would get if you sample from your sample. Or more formally, if you have an order statistic, so if you observe x1, x2, xn and you order them as y1, y2, yn from an observed random sample, then the empirical distribution function is defined as the sum of IID random variables, where I is f and t, which is equal to 1 over n, sum of indicator functions e less than equal to t. The formula is actually easier to work than it looks, so let's just look at it what we are doing, and we can do this in R with the ECDF function, or we can do it from scratch. So I am looking at a data set which is called ROC data set. It contains 48 measurements, and we'll talk about plotting that. But before that, let's just do it for a very simple data set. Let's say it has, let's say we observe 0, 4, 2, 2, 1. First thing you do is sort. That's what is called the ordering of statistic y1, y2, yn. And then you only look at the unique values. What are the possible values, right? So there are 4 possible values because 2 is repeated twice. And then the possible values, so then what you have, 0, 1, 2, 4, those are your possible values. The probability of getting 0 is 1 in 5. Probability of getting 1 is 1 in 5. Probability of getting 2 is 2 in 5. And probability of getting 4 is 1 in 5. So that's the probability, and then you just accumulate them. 1 and 5, and then 1 and 5 plus 1 and 5, which is 2 and 5, plus 2 and 5, 4 and 5 and 5. So that's your cumulative probability distribution for this one. And then you can plot the ECDF of A and see that it is giving you the exact same thing that you have here. So when it's 0 to 1, right, 1 or less, it's 0.2. Then it goes to 0.4 as it's in your table. Then it goes to 0.8. That's what you calculated here, and then it goes to 1. So that's exactly, so when you plot the ECDF and R, it is doing what you are actually can do manually this way. That's what is happening inside it. So let's look at a bigger data set, because otherwise if this is very small data for illustration purpose, it's not going to give you a good picture of when you're trying to compare. So the empirical CDF of area variable from the data rock. You can look up on this data by doing a question mark and rock. So you plot that, and this is how the empirical CDF looks like. Looking at the plot, we can see the estimated probability that the area of sample is less than or equal to, let's say 8,000, is about 0.6. But we don't have to rely on eyeballing the graph. We have a function, we can use it to get more precise estimate. So you wanted to see what is the empirical CDF at 8,000, it's actually 0.625. You can see it at different values. There is also summary methods for ECDF, so you can find what is the minimum, maximum, and all those values, and you can compare them with the summary of the actual data. Now the key thing that you will be doing throughout this course is superimposing empirical CDF with theoretical CDF. For example, could our data be thought of as coming from normal distribution? So what do? You plot the ECDF and then you superimpose it with the normal distribution curve. That is the red curve, elongated S. It looks pretty much, the points look pretty much similar to the red, what a normal CDF would look like. So it seems like the lines overlap quite a bit, suggesting that the data can be approximated with normal distribution. We can also compare the estimates from our ECDF with theoretical CDF and see. So P norm at 8,000 with mean of whatever is the mean of that data, and standard deviation as the standard deviation of data. It's 0.618, and the P norm that we calculated with empirical CDF was 0.625, pretty close, right? So I'm going to give you another example which will come in handy for later use. So here we have observer data, a random data that I have generated using normal distribution. And now, so I observe this data V, which is actually square of standard normals. So V should, for me, is a chi-square. Now I want to see if it actually really is a chi-square. Like, this is just because I generated, so I already know it's chi-square. But let's say I just had this V, I observed V, and these are all positive numbers. So I'm thinking maybe let's fit chi-square, and I fit a chi-square maybe with 1 degree of freedom, and then another one with 2 degrees of freedom. And we can superimpose that. So you can use these two little code chunks to generate graphical, certain graphs to graphically assess whether, so the histogram is the histogram of the data that you have observed. The red plot is the plot of the empirical density curve, and the green one is the theoretical density curve. This one is in this one it's just the two chi-squares with 1 and 2 degrees of freedom. This one, the red one, is the empirical density, and the green one is the theoretical density. And do they look like very similar to chi-square? Does your histogram look similar to that? So that's one way of assessing whether it's something that would fit follow certain distribution, what you have observed. Another way of assessment is QQ plot, and you can go to this link and check out more on them if you're not very well aware of QQ plots. They do the same thing. basically. So what the idea of this lab is to make sure that you understand that when you observe a variable like a sample and you have certain reasons to believe that that sample follows a particular distribution, you can always create a histogram. You can you can plot empirical density and you can superimpose it with the theoretical density that you believe it might follow to compare the two plots and see if it works or it doesn't work used graphically. So this is a very important tool of graphical comparison.